Hello friends, we have been successfully able to navigate from the process of combination to the process of concentration. Now the intermediate steps that enabled us to rather logically translate from or move from the combination to that of concentration is the process of classification. And even in this combination, we had one process called screening, which even though is a part of the combination or liberation, the role of screening was not fragmentation but rather separating the particles, the mixture of particles based on their sizes. However, these particles, they were fed back into the process of or fed back into the events that are associated with liberation or combination. The smaller particles that were separated through screening, it was fed into those smaller particles are fed into the grinding mill, whereas the larger particles are fed back into the tertiary crushing. So the screening in the framework of the liberation, it essentially introduces a closed loop or a closed circuit. Now there is a similarity between or the transition from screening to classification is more or less smooth, because classification, as we saw, is rather an advanced form of screening. While in screening, the process is rather straightforward. You have the interaction of the particles within themselves, and more importantly, the interaction of the particles with the screens. And depending on the size of the particle, either this particle will pass through the screen or they are withheld by the screen, and therefore we are able to separate these particles based on their sizes. Now, classification, like we said, is more advanced form of screening. Here, the particles, the mixture of the particles of different sizes, they are allowed to interact with a fluid. This fluid is often dynamic in nature, and it can be driven by a specific accelerating force. This movement of the particles, they can be influenced by a specific accelerating force like a centrifugal force, or it can be allowed to interact with the gravitational force itself. So irrespective of what the accelerating force is, the classification involves the interaction between two counteracting forces. One is the accelerating force that ensures a specific movement of the particles, and there is a counteracting force that is introduced by the fluid through which these particles are propagating. And the combination of these two forces, it offers the particle a constant velocity we refer to as the terminal velocity. This terminal velocity of the particle in the medium, because of the counteracting forces, depends on the mass of the particles. And when we say mass, it is the combination of the size and density. And depending on these terminal velocity, it is possible for us to classify these mixture of particles depending on the velocity that they assume. And this classification helps us smoothly move into the process of concentration, wherein we are not interested in the features of the particle. Unlike screening, we are not interested in the size of the particles, and unlike classification, we are not interested in the mass of the particle. What essentially we are interested in is separating the gangue from that of the minerals. So that is the main purpose of the classification, or rather concentration, pardon me. So when you compare these two, screening and classification, to that of concentration, even though a specific form of concentration might share some traits with the screening and the classification, when you look the fundamental reason of why these processes are being pursued, when you consider the reason why one has to do one has to follow, or one has to expose the mixture of materials or mixture of particles to screening, classification and concentration, the concentration has its unique goal. The concentration intends to separate the mineral particles that we desire from that of the gangue particle. Now, not all the concentration process or not all the concentration techniques, they share a similarity with classification and screening. It is one form of the concentration technique that shares the similarity with the concentration and screening, that is density separation, or rather, more precisely, that is gravity separation. So So it is this form of concentration, the gravity separation, this form of concentration is the one that has some similarity with the process of screening and classification. So in case of gravity separation, the fundamental goal is using gravity, we are intending to separate the gangue from that of the minerals. And the mixture of particles that we intend to handle through this gravity separation process, the mixture of particles that we intend to separate through this gravity separation process needs to have a unique feature for those particles, those mixture of particles to be handled or to be efficiently handled by the gravity separation process. So not all mixture of particles can be efficiently handled by gravity separation process. There need to be a specific feature associated with this mixture. So the mixture now comprises of gangue and mineral, and it is our goal to separate gangue from that of the minerals. Now, not all this separation cannot be, or gravity separation cannot be imposed on all these mixture to achieve this separation. So there needs to be a specific criteria that needs to be fulfilled for the gravity separation to be efficiently used in distinguishing or in separating gangue from that of the minerals, and that feature is the density. So only when, because of its chemical composition, because of its chemical makeup, when the difference in the density between gangue and mineral is sufficient, we will be able to use the gravity separation process. So we saw that there is a smooth transition from, it is possible for us to have a smooth transition from combination to concentration, but we are not speaking about all the processes that are involved in the concentration, but we are restricting ourselves to a specific process of the concentration, that is the gravity separation. Now gravity separation can only be imposed efficiently when the difference in the density between gangue and the mineral are significantly higher. Now, we saw in the previous lecture, or towards the conclusion of the previous lecture, we saw that there are certain advantages of using gravity separation or adopting gravity separation when compared to other concentration techniques. Now, while introducing the process of concentration, the different processes that are involved in the concentration or different techniques that one can use to concentrate your given mixture, there are several processes that are involved. There are several techniques one can adapt. Now, amongst all this, gravity separation has a unique advantage associated with it. One is the gravity separation process is rather economical. The reason it is economical, primarily because we are using as an accelerating force a force that is readily available in the nature. So you have to spend only money, or you have to spend only to get rid of this force. Otherwise, the force is always available with us. So essentially what we are doing is we are making use of a force that is available to us readily and using that force to our advantage. So that, in that sense, the gravity separation process is economical. You need not have a separate setup or a separate equipment in order to introduce the force that is required for the separation process. In order to introduce the accelerating force, you need not have a separate equipment or a separate contraption. The other advantage is that, similar to, since classification also, when you consider classification that is operating using the gravitational force, and classification is able to, or is a refined form of screening, the gravity separation is also able to handle minute particles. Of course, similar to that of the classification, there is particularly the one that is associated with the gravity, there is a size limitation. Even in the gravity separation, there is a size limitation, but for all practical purposes, the gravity separation is able to handle minute particles as well. So, even though there is a size limitation, what conventionally is referred to as the minute particle, what conventionally on an industrial scale, on a commercial scale, what is referred to as the small particles or minute particles can be elegantly handled using the gravity separation process. So what we essentially have is, we have an advantage from the particles that is being handled point of view, and also from the industrial scale, the scope of its usage. When we consider from that perspective as well, the gravity separation is advantageous to us since it's economical. So these two combination, because owing to this combination, the gravity separation is often preferred on an industrial scale for as a go-to concentration technique, provided that there is a significant difference in the density of the gangue and the mineral particles. when you have a mixture and you are fairly sure that the difference in the density between gang and mineral is quite huge, then you can go for the gravity separation process, and because you essentially you will be saving some amount of money because of through this process, and also you will be able to handle almost all the mixed particles of different sizes that are found in the mixture. Now, apart from these advantages, now when you want to quantify the efficiency, when you want to have an expression for the efficiency of the gravitation process, then we have to consider the feature that enables us to employ this process. So it enables us to employ this technique. Now what we essentially want to do is, we saw that, or we claimed that this gravity separation process can be efficiently used if and only if there is a significant difference between gang and the mineral particle. So that was our initial statement. So we saw that even though you have numerous concentration techniques that are available, it is possible for us to use gravity separation. Gravity separation is economical, and it has the capability of handling small particles. Now, because of these advantages alone, one cannot often go for the gravity separation. A specific criteria needs to be fulfilled in order for us to efficiently use the gravity separation process, and that criteria is based on the density, the difference in the density between gang and the mineral particles. So these are just statements. Now we want to quantify what is the efficiency of the gravity separation. Now again, since the efficiency depends on the density, the efficiency for the gravity separation process is expressed as the difference between the ratio of the difference between the heavy particles and the density of the heavy particle minus the density of the fluid or the liquid to that of the density of the lighter particles minus the density of the fluid of the liquid. So essentially what you have is the way we express the efficiency of the gravity separation process. It is nothing but the ratio of two terms. The numerator, it comprises of the difference between the density of the heavy particles. So this here is the density of the heavy particle, and this here is the density of the liquid or the medium. And so here, so we might have a confusion. So this here, Lig, this here is the density of the lighter particle, and this again is the density of the liquid. So you have the efficiency comprising of two different terms, ratio of the two different terms, and the first term is the difference between the density of the heavy particle. So this heavy, it can be either gang or it can be the mineral particle, and the same goes for the lighter particle. So the lighter particle can either be gang or the mineral particle, and it is not just the ratio of the heavy and the lighter particle, but it's the difference between the, we will see in a moment why we need to consider difference, but it is the difference between, when you consider the efficiency, it is the difference between the heavier particle to that of the density of the liquid. So density of the liquid and the difference between the density of the heavier particle and the density of the liquid to that of the density of the lighter particle to and the density of the liquid. So this relation is, enables us to quantify the efficiency of the gravity separation. Now the reason we want to consider the density of the liquid or the density of the fluid here in this expression, the reason we want to consider the density of the liquid is primarily because the behavior of the particles, even though it is dependent on its density, the behavior of the particle in a given medium, since it is the combination of the accelerating force and the resistive force, the behavior of the force or the behavior of the particle, it's influenced by the density of the liquid. Let me repeat. During the process of the gravity separation, what essentially we are doing is we are allowing the particles to settle down in a medium governed by the gravitation. So essentially we are allowing the particle to move in a medium governed by the gravitation. So essentially you have combination of a gravitational force that acts as the accelerating force. So you have a gravitational force that acts as the accelerating force, and you have a resistive force that is governed by, that is introduced by the fluid. So you have these combination of these two forces, an accelerating force and a resistive force. Now this accelerating force, the factors when you have an accelerating force, the feature of the particle that governs the behavior of the particle under the influence of the accelerating force is the density of the particle. So depending on the density of the particle during gravity separation, what you essentially have is you have a specific behavior of the particles. When you have a particle and during gravity separation, its behavior is largely governed by, when you don't consider the resistive force, it is largely governed by the governed by the feature of the particle, that is its gravitation. So depending on the density of the particle, be it heavier particle or be it lighter particle, depending on its density, the behavior of the particle under the influence of gravity varies in a given medium. Now we need to also consider the resistive force that is introduced by the medium, because the behavior of the particle is not just influenced by the accelerating force, but it is also influenced by the resistive force. So we need to consider the factor that governs the resistive force, and here in this case it is the density of the liquid, or the density of the medium, or the density of the fluid. So you have the accelerating force which influences the particles through the gravity or through its cavity, and we have the resistive force that depends on the density of the fluid, the density of the liquid. So therefore, when we say the behavior of a particle in a medium during gravity separation is the combination of accelerating and resistive force, what essentially we are talking about is the behavior of the particle during gravity separation is the difference between the density of the heavier particle minus the density of the lighter minus the density of the medium, and similar to that of the density of the lighter particle in relation to the density of the fluid. So the behavior of the heavier particle in a given medium is influenced by this term here. The behavior of the lighter particle in a given medium, when you have the combination of accelerating and the resistive force, is influenced by this term here. So whenever you want to quantify the behavior of an heavier particle or the lighter particle, you need during gravity separation in a given medium, you need to consider the density of both the particle and also the density of the medium, because it is through the density of the medium we are accounting for the resistive force. So essentially these two terms govern or dictate the behavior of the particle in the medium under the gravitational force, and the efficiency of the separation in the efficiency of the gravity separation, which is dependent on the difference between the gravity of the heavier and the lighter particle of the mineral in the gangue, is now correspondingly expressed as this relation here. So this is a conceptual understanding of how we arrive at this relation. So density of the heavier particle, density of the lighter particles, and we have the density of the liquid that accounts for the resistance that is influenced or that is introduced by the liquid. Now we can have efficient gravity, or one can employ the gravity separation process efficiently when this ratio here, this efficiency here, is greater than 0.25. So the gravity separation process, or rather it's greater than 2.5. So the gravity separation process can be efficiently employed when the ratio here is of this particular value. When you have the efficiency or the difference in the densities, and that involves the density of the heavier, lighter and the liquid, when this ratio is greater than that of, when it's greater than 2.5, then we can safely say that for this mixture the gravity separation can be adopted and it will be efficient one. Now what essentially we have seen is, we have seen a way of quantifying the gravity, or we now have an expression that rather quantifies the gravity separation, or the efficiency of the gravity separation process, and it helps us rather understand, or it helps us choose for which, or it helps us select rather reasonably which mixture of particles can be treated using gravity separation process. So this expression here, it serves two purposes. One, it helps us understand the efficiency of a gravity separation process, and it also helps us make a reasonable choice for a given mixture, or reasonably choose a given mixture for to be handled through the gravity separation process. Now when we are talking about the efficiency in this context, the efficiency of the gravity separation process, which is exclusively governed by the density of the particles and the density of the medium in which these particles are suspended, we are actually overlooking if you consider rigorous treatment of the efficiency, then essentially in this expression here, it overlooks one factor. What the efficiency, in this expression of the efficiency, one factor that it overlooks is the size of the particles. Now this expression here, it exclusively considers the density, but what it overlooks is the size of the particle. Of course, you could argue that whenever we are considering density, which is nothing but the mass by volume, and in volume you have the size is in a way included in the volume. One could argue that, but what we mean by size is we are not treating size, or we are not treating the shape or the morphology or the size of the particle in terms of its contribution to the density. What we are essentially considering is size in terms of its ability to propagate or to move within a given medium. So when we say that this expression of efficiency does not include the role of size, this expression of efficiency is rather simplistic. It overlooks one feature of the particle, that is size. What we mean by that is we are not talking in terms of the contribution size makes to that of density. What we are talking about is the natural flow of a particle owing to its size. So depending on the size, the particle of same density will exhibit different movement. So if you have two different particles suspended in a given medium, they are of same densities. Depending on the size and the morphology of the particle, they exhibit different movement. Again, we saw that in case of screening, that when you have particles of larger sizes, they tend to occupy the surface of the screen, whereas the smaller particles, they get suspended above the larger particles, and that's the reason we introduce stratification during the screening discussion. Stratification process while discussing screening. So depending on the size of the particle has its natural tendency to exhibit a specific form of a movement. So that role of size, so depending on the size of the particles, as we saw in screening, there is a specific way a particle would move in a given medium. So that is not considered in this efficiency framework. So therefore, even though while considering the efficiency, even though this simplistic form, or rather this straightforward expression for efficiency will enable us to understand the efficiency of a given operation, that is one purpose itself, and will enable us to choose a specific mixture to be handled through the gravity separation process. Even though those things can be, for those things we can employ this efficiency expression, we cannot precisely for sure state that all the features that govern the movement of the particles in a given medium are accounted for in this expression here. So one factor that is missing in this rather straightforward or simplistic expression of the efficiency, or the go-to expression of the efficiency, is that it ignores or it overlooks, it assumes that the movement of the particle, it does not depend on the size. It assumes that irrespective of the size of the particle, the movement is entirely governed by its density. It does not assume, or it does not consider the fact that certain particle or certain sizes, certain morphology enables the particle to move freely when compared to other sizes and other morphology. So those aspects are not considered in this efficiency expression. However, this does not mean that this efficiency expression is rather not so relevant. This efficiency expression, despite being simpler, it is highly relevant on an industrial scale, on an industrial setting, primarily because it helps us make a reasonable decision on if a particular mixture can be handled through gravity separation or not. And if you have an existing gravity separation equipment or process that is running, this expression helps us to calculate or estimate its efficiency and to a certain degree of accuracy. So this is one rather limitation of this efficiency expression here. Now, given that there are certain particles that limit, so when you consider the overall advantages of the process that of gravity separation that we have been considering, when you consider the overall advantages, we saw that it is economical, and there is specific, or there is, when you consider the particles that largely constitute the mixture, then even in these particles, the smaller size range particles can be elegantly handled by the gravity separation process. And since it is possible for, when you consider the mobility of the particles in a medium, it is possible, as like we are considered, because of their small sizes, these particles, even though they can be handled using gravity separation, they need some stratification to be included such that their mobility is also on par with the mobility of the small size particles is also as sufficient or as adequate as the large size particles. In some instances, this accelerating force, the gravitational force that acts as the accelerating force in the gravity separation is augmented with the centrifugal force. So what essentially we have is, now we saw that there is a specific advantage associated with the gravity separation, that is, it is economical and it is able to handle a wide size range of particles. Now when we consider this its efficiency, even though it enables us to make reasonable choices, what it does not include is, it does not include how the mobility, the behavior of the particle is influenced by its size. Now despite its lack of, or its the lack of inability of this efficiency expression to encompass the role of the size and how it governs the mobility of the particle, we need to capture its mobility sufficiently during the operation. Even though the efficiency expression is not able to capture the role of size and its influence on the mobility or the movement of the particle, we must ensure that it is not overlooked during the process. It is not rather relaxed, or it is not compromised during the process. We need to ensure that these small particles, these relatively small particles, also experience sufficient degree of movement so as their entire separation is based on density. So in order to do that, in order to ensure that even though these small size particles on its own, by their nature, they do not move as easily as the large size particle, in order to propel their movement, in order to enhance their movement, an additional force is included, an additional accelerating force is included, and that force is often the centrifugal force. So essentially, even though there is a limitation associated with this expression, this rather straightforward expression for the efficiency, even though this expression here does not consider the influence of the size of the particles on the movement of the particles in a suspended medium, in order to ensure that these small size particles also behave, also move similar to that of the large size particle, an additional accelerating force is introduced, and often that is a centrifugal force. So even though the whole process is fundamentally governed by acceleration due to gravity, it is fundamentally governed by the gravitational force, and therefore we refer to it as the gravity separator. We at times include the centrifugal force in order to ensure that the smaller size particles also adequately move similar to that of the larger size particle. So this depends again on the nature of your mixture, and you find that in your mixture you have considerable amount of smaller size particle. In order to increase the efficiency of your gravity separation process, you include the centrifugal force. So again, after quantifying the efficiency, now to further improve the efficiency, particularly when you have a mixture with a large fraction of the smaller size particle, you augment your gravitational force with centrifugal force in order to ensure that you are able to achieve the sufficient amount of separation, and its efficiency is ultimately higher. Now, before getting into the unique techniques that are adopted for this gravity separation, let us consider the one preparatory step that is invariably performed before the gravitational separation is adopted. So what essentially we want to do is, so far we have been considering the theoretical aspect of gravity separation. What are the factors that are involved, what are the advantages associated with it, and how one can quantify the efficiency of the gravity separation process. Now what we want to do is, we want to get into the specific techniques that are involved in the gravity separation process. So before getting into the specific ways the gravity separation is employed for a mixture of particles, let us consider one preparatory step that is important. This preparatory step is referred to as the de-slimming. So invariably, when you want to expose a given mixture of particles to gravity separation, you need to prepare that mixture, and this mixture needs to be deslimmed. So what we mean by deslimmed is we need to identify a category of particle in this mixture which can be referred to as slimes. So we need to separate out a category of particle in this mixture. So a mixture is going to be fed into, or it's going to be treated by gravity separation, and this mixture as a preparation, what essentially we want to do is we want to remove certain category of particle in this mixture so that the efficiency of the gravity separation process is sustained. So the gravity separation process is efficiently employed. In order to do that, in order to ensure that the gravity separation process is efficient, we need to do some preparation, and in that preparation involves removing a specific category of particles, and this category of particles are referred to as slimes. Now, what these slimes are is, these slimes are the particles with sizes which are less than the size that gravity separation can handle. Supposing, say, Dcritical is the maximum size that can be handled by the gravity separation process. So Dcritical is the size, maximum size that gravity separation can be, the process of gravity separation can handle. Now, this size in itself is quite smaller. However, unfortunately, because of the preceding processes, there are particles which are even smaller than that of this Dcritical here. So you have Dcritical, let me write it more legibly. So you have Dcritical, which is the maximum size the gravity separation process can be efficiently handled. And there are particles, because of the preceding operation, preceding techniques or preceding processes, that the size of which are smaller than that of the Dcritical. Now these particles cannot be elegantly handled, they cannot be adequately handled in the gravity separation process, even after augmenting the centrifugal force. Again, the role of the centrifugal force is, it is to improve the efficiency, but it is not to ensure that the smaller size particles are included, but to ensure, the role of the centrifugal force is to ensure that the smaller size particles, the particles in the range of Dcritical, exhibit the same amount of movement like that of the larger particles. That is the role of the centrifugal force. Now, when you consider the mixture in a realistic scale, what happens is there are particles that are smaller than the maximum size that can be handled by the gravitation separation process. So these particles needs to be removed, or else what would happen is these particles, they get mixed up with, or they get completely mixed up, or they get, in one sense or the other, they get suspended and dissolved, or apparently dissolved in the medium, and thereby increasing the density of the medium, and thereby interrupting with the overall density or overall efficiency of the process. So what essentially these slimes do is, these slimes, because of their minuscule size, because of their very much minuscule sizes, because of their you could say microscopic sizes, what they do is they tend to suspend it, or they tend to get suspended in the medium in such a way that the overall density of the medium, the overall density of the liquid gets varied, it gets changed, it gets increased. So therefore, in order to avoid such change in the density of the medium, in order to avoid such reduction in the efficiency of the process, in order to ensure that the medium that we feed in does not get contaminated by this slime, we prepare the mixture that is going to be treated through the gravitation process, and we deslim it. So essentially what deslimming is, identifying the slimes. These slimes, these are the criteria for differentiating the slimes is here. So these slimes are essentially smaller than the maximum size that can be handled by the gravity separation process. So once you have identified these slimes, so these slimes are removed as a preparatory process for the gravity separation. The process that is often adapted to ensure or to deslim a given mixture, the process that is often adapted is the technique that is adapted is the hydrocyclone or the classification process. So even in the so essentially the classification, or more precisely the hydrocyclone technique, is adapted to prepare a given mixture for the gravity separation. So through hydrocyclone, by adopting this hydrocyclone or feeding in our mixture through the hydrocyclone, what essentially can be done is we are able to rather remove the slimes from that of the mixture that are fed in. And after deslimming, we are now in a position to be able to separate the can from the mineral using gravity separation. Now, rather technique that uses this gravity separation to concentrate a given mineral is referred to as jigging. So jigs are an equipment or a setup that largely employs, that fundamentally is governed by the principle of concentration, and this jigs through the principle of the gravity separation ultimately facilitates the separation of the mineral from that of the gangue. Now the overall process of jigs can be understood by the schematic representation here. So what essentially you have here is, you have a setup, a simplistic setup that allows for the movement of this picture here upward and downwards. So what we are essentially trying to do is, we are essentially trying to understand the principal operation of the jigs. Now the principal operation, how the jig operates, can be understood by considering the schematics here. Now one key thing you could observe is this schematic. It comprises of a setup that enables the upward and downward movement of this mixture here. So of course the mixture of, again, gangue and the minerals here, they are present in a specific ore box. So these are present in a ore box, and again, depending on the density, one could be referred to as the lighter particles and other could be referred to as the heavier particles. The reason why we are not again referring to the terms mineral and gangue is because in some mixtures the gangue could be the heavier particle, in some mixtures the gangue could be the lighter particle. So in this context of separation, particularly the gravity separation, in this context of concentration, what essentially we refer to as the two categories of particle, we refer to it as the light and the heavier particle. Now what you have is, during jigging, so the apparatus here represents the operation or the schematic, it helps us understand the operation of the jigs, and the process itself is referred to as jigging. Now as the one characteristic feature we saw is the ores, the mixture of the particles, they are present in the ore box, and this ore box is allowed to move upward and downward in a medium that is usually water. So this ore box is suspended in a medium, and in this medium and in this overall this setup is allowed to move upward and downward. During the downward movement, what essentially you have is, you have the flow of water. So when you allow this box to move downwards, you allow the water to enter through the ore box through the jig skin here. So the reason you need to have the movement of the ore box is, what essentially you are achieving is, you are achieving a pulsating movement of water, or the pulsating movement of fluid. So the upward and downward movement of the ore box, it allows us to have a pulsating movement of the fluid, which in this case is the water. Now when you allow the box to move down through the jig screen, the water will move up, and when you remove the water from when you move the ore box above, all the water that have moved in to the ore box will be removed from the ore box. So that is essentially what this jigs achieve. So essentially what jig does is, jig allows the particle to behave in a specific manner in response to the pulsating movement of the water. So this pulsating movement of the water will allow the particle of different density to behave differently, thereby allowing us to separate the particle based on their behavior. So essentially what happens in jigs is, you introduce a pulsating movement of a fluid, and this pulsating movement of the fluid is achieved by upward and movement of the ore box. So we need to have the primary governing factor is the pulsating moment of the fluid, and this pulsating moment of the fluid, unlike in case of hydrocyclone wherein we had a specific apparatus that will give us a spiral movement, in this case the pulsating movement is achieved of the fluid is achieved by upward and downward movement of the ore box. When the ore box moves downward, the water moves upward, thereby suspending the particles in the water. And when you remove the water and when the ore box moves above, then the water that filled the ore box will gradually recede. So that is what happens during the process of jigging. So essentially in jigs, what we attempt to do is we attempt to facilitate the movement of the particle based on the pulsating movement of fluid. And this movement of particles, since in response to the pulsating movement of fluid, since it is dependent on the density, we are able to separate these particles based on their density. Now, when you consider the different movement, this particular movement of the particle that enables us to have the pulsating movement of fluid, this upward and downward movement of the ore box that enables us to have the pulsating movement of the particles, they have specific name associated with it. The downward movement of the ore box that allows the water to move into the ore box is referred to as the pulsion movement, whereas the upward movement of the ore box that removes the water from the ore box is referred to as the suction movement. Now essentially what we have is in jigging we have two movements, downward and upward movement. This combination of these two movements introduces pulsating movement of the fluid. The particle behaves in response to this pulsating movement of the fluid. Since this behavior is dependent on the density, we are able to separate the particle based on this density. Now the terminology that is used for the upward and downward movement of the ore box is pulsion and suction. The pulsion is the downward movement of the ore box, which allows the particle or which allows the water to occupy the ore box, and the suction movement, it removes the water from the ore box. Now if you consider the behavior of the particle during the pulsion and suction movement, it all depends on how much time we allow the suction or the pulsion movement and how much time we allow or how much time we spend in the suction movement. So what we mean by that is the way the particle behaves in addition to that of its density, in addition to that of its size, when you consider from the perspective of the operation of a jig. So when you consider the operation of a jig, you are not governing the behavior of the particle. You are essentially governing the pulsion and the suction movement. The way we are able to operate the jig, the way we are able to ensure that the jig is efficiently operating is by considering just the pulsion and the suction movement. The way one can then ensure the behavior of the particle is by governing how much time is being spent on the pulsion process and how much time is being spent on the suction process. So depending on the how much time pulsion and suction movement takes, the behavior of the mixture of the particle correspondingly vary. So essentially what we are now saying, just to have a quick recap of the operation of jigging. So the process of jigging, the technique of jigging, what it essentially does is, again similar to the overall description of the gravity separation, what it essentially does is it essentially wants to separate the particles based on its movement to a given dynamic fluid under the presence of a dynamic fluid. And this dynamic fluid is a pulsating water in case of a jig. And what the way we achieve or the way we ensure that the water is dynamic is not by moving the water, not by moving the medium. In case of hydrocyclone, we moved the medium. Here we are not moving the medium. In case of jigs, we are moving the ore. We are moving the particles through the ore box, and we are exposing the particles to a dynamic medium. And this movement of this upward and downward movement of the ore box, it is referred to as the upward movement is referred to as the suction, and the downward movement is referred to as the pulsion. So this is the way, or this is the operation of a given jig. And when you consider the process that is involved, the process is similar to that of the one that is generalized in the gravity separation process. That is, here again we have the particles behaving differently in response to a dynamic fluid. However, the key difference is the dynamic nature of the fluid is not because the fluid is moving, but because we are allowing the particle to behave, or the ores to behave in such a way that it appears the fluid is, there is an apparent dynamic nature to the fluids. Now we saw that the only way for us to control the efficiency, or the only way for us to control the behavior of the particle is through the upward and downward movement. So it means depending on the time we spent in the upward and downward movement. So it can be immediate upward and it can be immediate downward, or it can be a gradual downward and a gradual upward. So all this is dependent on the time. So depending on the time, we will be able to govern or dictate or rather influence the efficiency of the separation through gigs. So in order to understand that, how this upward and downward movement of these jigs help us in or facilitate or help us in dictating or governing the efficiency of the overall operation, we need to study how the particles behave or how the particles move under this setup. Now, when you consider a system wherein we have a dynamic fluid that is moving, it is rather straightforward. We just need to compare the forces that is offered by the dynamic fluid and the forces that is offered by the accelerating force. So we need to just compare these two, and then we can say, okay, in response to this combination, you have a specific moment of the particle. So that is rather straightforward when you have a dynamic fluid flowing at a specific direction. However, in this case, we have a combination. We have an apparent dynamic fluid. Essentially, we are moving the overbox in such a way that the static water or the static fluid is made to appear dynamic. So in this case, when we want to understand the behavior of the process, behavior of the particle, this whole setup is quite unique. This whole setup is nothing like what we have considered so far. So therefore, we need to spend some time on understanding how particles would behave for a setup like this, wherein it is not exclusively dynamic, but it is apparently dynamic. So this we will see in the next lecture. So in the next lecture, what we will essentially see is how, in response to this downward and upward movement of the overbox, in response to this pulsion and suction action, the particles of the different sizes and density behave. So with this, with this generalized understanding of how the jigs work, or what is the operation behind the jig, and what is the different movement that is associated with the jig, we will wind this lecture up, and in the next lecture we will try to understand how, in response to this movement, the particles behave. Goodbye.